Welcome to a new class of organic chemistry. In this video class, we are going to discuss 6 points on pyridine. So let's see. First point, pyridine is a 6-membered heterocyclic ring containing nitrogen, the molecular formula of which is C5H5N. Point number 2, pyridine has a conjugated system consisting of 3 double bonds and 3 single bonds. Needless to say that the 3 double bonds and the 3 single bonds are arranged in an alternating fashion. Point number 3, pyridine is an aromatic compound. The reason pyridine is aromatic is because it fulfills the 4 conditions of aromaticity. Condition number 1, the molecule should be cyclic. In pyridine, the first carbon atom is attached to the 5th carbon atom. That means pyridine is a cyclic molecule. Condition number 2, the molecule should be planar. If you look at the structure of pyridine, each of the carbon atoms of pyridine is a doubly bonded carbon atom. For a double bond to appear between 2 carbon atoms, the 2 carbon atoms should undergo sp2 hybridization and there should be an unhybridized p orbital in each of the carbon atom such that they overlap and form the pi bond or the double bond. As there are 5 doubly bonded carbon atoms, that would only mean that there are 5 sp2 hybridized carbon atom. Now, after a carbon atom undergoes sp2 hybridization, the groups that are attached to the carbon atom, they assume the farthest positions available in space, and that would lead to a trigonal planar geometry around the central sp2 hybridized carbon atom. Now, each of the 5 carbon atom, which is an sp2 hybridized carbon atom, have this trigonal planar geometry. That would only mean that the carbon and the hydrogen that are attached to it are in one single plane. That means the molecule of pyridine is a planar molecule. Condition number 3, the molecule should be conjugated. As we can see, after every double bond, there appears a single bond. The molecule of pyridine is no doubt conjugated. Secondly, there is a possibility that the pi electron may get delocalized to the adjacent position. If it gets delocalized, that would mean that the molecule is aromatic. But does that delocalization takes place? For this, we have to apply Huckel's rule. Huckel rule is 4n plus 2 pi rule. You write 4n plus 2 is equal to 6 resonating electron. 1, 2, 3, 4, 5, 6. 6 resonating electrons of the pyridine. 4n plus 2 is equal to 6. Subtract 2 on both sides. That would lead to 4n is equal to 4. N is equal to 4 by 4, which is 1. 1 is not important. What is important is n is not a fraction but a whole number. If you get n as a whole number, that would mean that the molecule under consideration is compliant with Huckel's rule. That is, delocalization occurs in the molecule, and that is that the molecule is aromatic. That means pyridine here has been proved as aromatic. Point number 4, the true structure of pyridine, note the point, is not the Kekulé structures but the resonance hybrid structure of pyridine, which is a combination of 5 resonating structures of pyridine, of which structure number 1 and structure number 5, the Kekulé resonating forms, have a major contribution towards the resonance hybrid structure, while structure 2, 3 and 4, the ionic resonating forms, have a lesser contribution towards the resonance hybrid structure. That is to say that pyridine spends most of its time as Kekulé resonating structure, structure 1 and structure 5, while it spends lesser time as ionic resonating structure 2, 3 and 4. But why is it so? Why is it that pyridine spends less time as ionic resonating forms? If we introspect structure 2, 3 and 4, the ionic structure, we would notice that there is charge separation in these structures. Charge separation requires additional energy, and because it requires additional energy, that puts these three structures at a thermodynamically higher energy level, while the structures 1 and 5 are at thermodynamically lower energy level. As for pyridine, it would prefer to spend its time at thermodynamically lower energy level, and it is for this reason that structure number 1 and structure number 5, the Kekulé resonating forms, have a major contribution to the resonance hybrid structure of pyridine. Point number 5. Pyridine undergoes electrophilic aromatic substitution, but under vigorous conditions. There is no doubt in anyone's mind that pyridine is a benzenoid compound. Being a benzenoid compound, it is rich in electrons. But there is a problem. We have a nitrogen here which is electronegative. And this electronegative nitrogen pulls an electron pair from the adjacent positions, and this creates scarcity of electron, particularly at ortho and para positions. Now, if an electrophile is given an opportunity to attack the pyridine ring, it would not do so. Why? As it is not attracted by pyridine ring, owing to the positive charge on the pyridine ring. Therefore, an electrophile would not attack pyridine ring at normal conditions. However, at vigorous conditions, it would do so. In contrast, if the electrophile is given an opportunity to attack the benzene ring, it would do it instantly because benzene is a rich source of electron. Point number 6. Pyridine undergoes nucleophilic aromatic substitution with ease. We already discussed that there is a scarcity of electron, particularly at the ortho and para positions of pyridine. This scarcity of electron is because of the electronegative nitrogen pulling the adjacent electron pair towards itself. If a nucleophile is provided with an opportunity to attack pyridine, it would definitely do so at the ortho and the para positions. In contrast, if the nucleophile, which is rich in electron, approaches benzene ring, then as it approaches, it would be repelled because benzene itself is rich in electron. Dear students, I hope you have liked and I hope you have understood the class. If it was useful for you, please do not forget to like, share and subscribe this channel. Thank you very much.